Here we go. So, you know, where are we in our description of the behavior of electrons? Well, electrons are weird, man. They have a weird behavior and they have weird motion, and we actually need an entire branch of physics dedicated to just describing the motion of electrons, right? And what electrons are doing in atoms. And that is called quantum mechanics. Um, Electrons can act as particles, and they can also act as waves. Light and electrons are like the only things in nature that can kind of act like matter particles one moment and act like energy light the next moment. They call it wave particle duality. Nobody really understands it, but we sure do have some equations that can do some things with it. Um, so in order to understand what we are going to talk about tonight, we need to talk about the nature of light, which is a form of energy, right? Because you are not going to understand Bohr's experiment until you understand the wave nature of light, okay? The fancy word for light is electromagnetic radiation. And electromagnetic radiation has an electrical and a magnetic component to it. Now, you don't really have to worry about the magnetic part of this. Um, but when you take physics, they'll talk about that in a little more detail. Um, Technically, when I say light, you probably think visible light, right? Red, orange, yellow, green, blue, indigo, violet, Roy G. Biv. But there's a lot more different kinds of light. Light is technically defined as anything that travels at the speed of light, which is 300 million meters per second, in a vacuum. And the entire, all different types of light, that's called the electromagnetic spectrum. And we're going to talk about that in a second. That's going to go all the way from radio waves to gamma rays, and visible light is just a tiny sliver in that section. But we're getting ahead of ourselves here a little bit. Let's first just talk about waves. So light is often best, and electrons at times, their behavior is often best described using wave model. And waves have some key parts. The first part is the length of a wave, how long it is. That's called its wavelength. And this can be measured a couple ways. One way to measure wavelength would be to go from crest to crest. You could also go from trough to trough, consecutive trough to consecutive trough. And then there is another way where the wave kind of gets cut in half. That's called the wave's resting position. Like if you imagine this was a string and you pulled it tight, that's where the string would be tight. And then if you move the string, that's what's causing it to oscillate. So where the wave crosses this resting position axis to where it crosses the resting position axis again and has the same slope, that could also be a measure of the wavelength, right? Now you got to make sure, because this has got a negative slope. So it's not this one that's got a positive slope. It's this one, which has a negative slope. Our symbol for wavelength is a Greek letter. It is the Greek letter lambda. It's kind of one of those and one of those. And one of those and one of those. And sometimes it comes back out better. Not all lambdas are created the same. You don't get the same make and model every time you draw it. Okay, anyway, there you go, right? Lambda. That is our symbol for wavelength. Amplitude is another part of a wave that chemists don't care about too much. Now, if you take physics, they might care a little more. Amplitude kind of tells you how tall the wave is. Now, for light, that tells you about brightness. For sound, that would tell you like how loud it is, right? Sound isn't even a transverse wave like this, but anyway. So we don't really care about brightness here in chemistry. We care about color and energy and speed. But anyway, that would be the amplitude. So we care more about wavelength. And then the other thing we care about is frequency. And frequency nowadays, we used to abbreviate it with a cursive V. Now we just abbreviate it with a lowercase letter f. Frequency tells you how many times a wave passes a point in time, usually per second. So like you would literally count how many wave cycles have gone by this point in time per second. So it's literally cycles per second, like 5 cycles per second, 15,000 cycles per second, something like that. And then in honor of a guy that did a lot of work with waves, they also call this a hertz. Hertz. All right. Cool. So here we have a pretty darn important formula, and I'm in fact going to write this. Let's just go to the board to do this because we'll use F's and whatnot for frequency. Let's first drill down on that frequency thing here really quick. Oh, I moved my camera because I set the projector up, so give me a second. Let me just, there we go. All right, that's a little better. So let's draw the wave here. So here's my resting position. And I'm going to start here, and we're just going to go. And I want to count, first of all, this would be my wavelength, lambda. And I want to count the frequency. So let's get the frequency. So we're going to count how many cycles we've got. So there's one, there's two, and a half, right? Because I would need another cycle. I'd have to do this. I've only got half of that. This wave would have a frequency of 2.5 hertz, or 2.5 cycles per second. Okay, so hopefully you can see how you would count that frequency. There's one, there's two, and this is a half. So it's a frequency of 2.5 cycles per second, or 2.5 hertz. Now, what's the relationship between the wavelength and frequency of a wave? Well, they are inversely proportional. If I shrink the wavelength, and I'll do this in a different color. If I decrease the wavelength, I will increase the frequency. So watch. I tried my best there to keep those wavelengths consistent. So look at my new wavelength for this red line. There's my wavelength. And my wavelength is much smaller, right? I tried to do about a half, right? So I don't know, maybe a little smaller than a half. Now look at my frequency. So if I measure the frequency for this red one, there's two, there's three, there's four, there's five, there's six, and there's seven. The red wave has a frequency of 7 hertz. So you can see how they are indeed inversely proportional. If the wavelength goes down, then the frequency goes up, right? Because if they're closer together, then they must be going up and down faster, right? So what is the mathematical relationship, though? Well, here's our formula, and you can write this a couple different ways. The wavelength is equal to the speed of the wave divided by the frequency. Now that speed, if it's light in a vacuum, that speed is 300 million, 3.00 times 10 to the 8, 300 million meters per second, 3.00 times 10 to the 8 meters per second. Now, obviously, you could rearrange this formula. We could write frequency equals speed over wavelength, and we could write speed equals frequency times wavelength. You got to pick one and memorize it, okay? Just pick one and memorize it. That's the one I memorized. Whatever works for you, right? Just memorize one, then you should be able to derive the other ones, or at least plug and chug and solve for what you wanted anyway. So let's try one of these. I think I have one in the slides here. So here you can see, much better drawn than what I drew, the relationship between wavelength and frequency. So, here, big wavelength, low frequency, only 4 hertz. Cut that wavelength in half, the frequency doubles to 8 hertz. Divide that wavelength by 2 again, and the frequency doubles now to 16 hertz. So there's the formula. Again, we use F's here. That's F equals C over lambda. I memorized in high school lambda equals C over F. Totally your call. So hang on. Did I have a problem on this one? Yeah. What is the wavelength of a wave traveling at the speed of light that repeats itself 7.5 times 10 to the 14th times per second? So why don't you try that problem there at the bottom? What is the wavelength of a wave traveling at the speed of light, 3.00 times 10 to the 8th meters per second, that repeats itself That's a fancy way of saying has a frequency of 7.5 times 10 to the 14th times per second. Go ahead. All right. Hopefully you use that beautiful E button on your beautiful calculator. So here we go. Lambda equals C over F. Lambda equals 3.00 times 10 to the 8th meters per second. Let's keep the units here, people. Right? Okay. We love the units. 7.5 times 10 to the 14th hertz. That's a cycle per second. A hertz is a fancy way of writing cycles per second. A cycle is just a word, it's not an actual unit. So you don't write the word cycles. What you can see here is if I take the speed in meters per second and I divide by the frequency in cycles per second, the seconds cancel out, and I'm going to be left with units of meters on my wavelength. Check your answer. Did you have units of meters on your wavelength? The next thing, two numbers in scientific notation, and I'm dividing. I hope you're using that E button. Big fan of the E button. I got 4.0 times 10 to the negative 7th meters. Now, a lot of times these wavelengths are very small, right? The wavelength of visible light goes from 400 nanometers to 750 nanometers. We'll talk about that momentarily. So what we often like to do is convert this to nanometers. So the next thing that I want, so a lot of times the wavelength of light is measured in nanometers. So the next thing I want to do is I want to write the conversion down. 1 meter is equal to 10 to the 9th nanometers. 1 meter is 10 to the 9th nanometers. And I want to convert this length from meters to nanometers. Well, how do we do that? I like to use dimensional analysis. So we're going to put that over 1. 1 meter is 10 to the 9th nanometers. And the beautiful thing about scientific notation is you don't even really need a calculator for this. If I multiply like bases, I add the exponents. So negative 7th plus 9 is to the positive second. So this is really 4.0 times 10 to the second, or 400 nanometers. Now, it's impossible to write 400 with 2 sig figs as a normal number, but I just wanted to show you that. Make sure that you can go from meters to nanometers. There are a billion 10 to the 9th nanometers in a meter. So this wave would actually be violet in color. A wave that's traveling at the speed of light and oscillating up and down 7.5 times 10 to the 14th times per second has a wavelength of 400 nanometers. And you'll see momentarily that's going to be our dark purples, very violet colors. All right, try this guy. Here we're going in reverse. And I'm giving you a wavelength in nanometers, so you're going to have to undo it. I'd like you to calculate the frequency of green light emitted by a hydrogen atom that has a wavelength of 486.1 nanometers. Imagine that it's traveling at the speed of light also. You can assume that. Let's assume we're in a vacuum, so 300 million meters per second for C. Give this problem a shot. All right, so here's how I would do this. Now, I have memorized the lambda equals C over F. So if it was me, I would do a little algebra. I would multiply both sides by the frequency. Then I would divide by the wavelength. And I would derive the formula I need, which is the frequency equals the speed of light divided by the wavelength. Now we have a problem. I can't just plug and chug this because my speed of light is in meters per second and my wavelength is in nanometers. So that's not going to work, right? Nanometers and meters. I need to convert that wavelength to meters before I can plug it in there. So how do we do that? Well, there's 10 to the 9th nanometers in a meter. Check this out. If you're really into scientific notation, 486.1 is really 4.861 times 10 to the second. And when you divide like bases, you subtract the exponents. So that's going to be 4.861 times 10 to the negative 7th meters. That's what's going to go down here, 4.861 times 10 to the negative 7th meters. Meters cancels out. I'm left with a frequency in per second, or cycles per second, or hertz. So 3E8 divided by 4.861 E negative 7 we get 6.17, 3 sig figs or 4 sig figs. Depends on whether or not you look at the speed of light as a measurement or a definition. Doesn't matter to me. I'll go with 3 sig figs, but I would take 4. 6.17 times 10 to the 14th cycles per second, or we could write this two different ways. We could bring that seconds to the numerator. You can bring any seconds up to you can bring any unit up to the numerator if you make its exponent negative. So we could write 6.17 times 10 to the 14th seconds in the negative first, or 6.17 times 10 to the 14th hertz. That's fine as well. So per second, seconds to the negative first, or hertz, any one of those, totally acceptable way to write a frequency. Cool. So how are we doing with those? Can we, if you have a frequency, can you get a wavelength? If you have a wavelength, can you get a frequency? Can you navigate around nanometers? Can you get out of nanometers? Can you get into nanometers? Those are the skills we just worked on there. So hopefully, because we spent so much time doing dimensional analysis, we spent so much time with the E button already. Hopefully we're not making like simple mistakes here, right? That's the goal. That's why we spend so much time in the beginning doing that simple stuff. Cool. So here's the full electromagnetic spectrum. So we scientists generally, and there's different ways to do this, but generally this is how we break up all the different types of light there are. And my guess is you've probably heard of all these before. So, visible light is just this tiny window here. This is all we get to see. When I say light, you probably think, red, orange, yellow, green, blue, indigo, violet, right? But there's other types of light. The lowest energy type of light is actually a radio wave. So, antennas, the old way we did television, right? Okay. That's all beams of light that get picked up by an antenna and then turned into sound or a picture or whatever, with a receiver, and they modulate the light different ways, or with either the amplitude or the frequency and then that's how they transport that information. Slightly higher in energy than radio waves or microwaves. So you know about microwaves because of microwave ovens. These are tuned to the vibrational frequency of water. So when you microwave food, it actually is just making the water molecules inside it wiggle and jiggle and jump around, and that's what heats it up. And then we have infrared. Infrared comes before the color red, like literally before red. Heat tends to fall in this infrared portion of the electromagnetic spectrum. So thermal energy, you actually right now are glowing, I know, but that's because you are emitting infrared light, right? So night vision goggles, that's what those tune to. You can pick up that infrared light. Then we got Roy G. Biv, and I need you to memorize this, folks. Roy G. Biv is from 400 nanometers to 750 nanometers. 400 being violet, 750 being red. Red is the lowest energy, so obviously we're increasing energy here as we go from left to right. So longest wavelength and lowest energy, and we're working our way towards shortest wavelength, highest energy, highest frequency light. So red is the lowest energy visible light, and violet is the highest energy with the shortest wavelength because the wave is going up and down faster. You should know this because what comes after violet? Well, ultraviolet. And this is where now the light is starting to get dangerous. When you go to the beach in the summer, or you spend a lot of time outside at the summer, or before you go to the pool, what do? Well, you put on sunscreen to protect yourself from ultraviolet light, UV light, and it's that UV light, that finally has enough energy now to damage, your skin cells. When you get a sunburn, it actually just killed that top layer of skin. What else was I going to say? Also, now you got enough energy to start mutating cells and changing DNA and causing cancer. So, ultraviolet is now finally high enough in energy that we're talking some serious energy now. After ultraviolet comes X-rays, definitely some serious energy there with the X-rays, right? Able to see through skin and muscles and all the way down to bone before it is reflected. And then finally, gamma rays. Gamma rays are the highest energy packet of light used, in cancer treatment, these high energy gamma rays, very targeted, specific, to kill like just the cancer cells. The Hulk, Bruce Banner got exposed to gamma rays. Look what happened to him, right? So there's our electromagnetic spectrum. What do you need to know from this? I would know the relative order, radio, micro, infrared, visible, ultraviolet, X-rays, gamma. And then I would definitely have the visible spectrum memorized from 750 to 400 nanometers. This is nanometers. And it goes from red to violet. Awesome. I'm happy with that. Cool. Cool. Okay, we got like a true or false. Which of these statements is true? So think about that electromagnetic spectrum we just went over. Which of those statements there is true? Right, hopefully you picked this guy. As energy increases, wavelength decreases and frequency increases. So that is exactly what we should have seen on this previous slide here. Ooh, no, two previous, right? You got your longest wavelength waves, a radio wave like ham radios, but you guys might not even know what that is. Ham radio is like longer in wavelength than AM radio. Used to be like a hobby. People used to like talk to. So ham radios have long enough wavelengths that they can bounce over mountains and stuff. You could talk to people across the globe. Like the waves could circumnavigate the globe. People would talk to people like in Russia and stuff with these ham radios. My mom's friend's husband growing up was a ham radio operator, and I remember this big thing in their living room, and he would sit there and he could reach out to people across the world. It's pretty crazy. No, I don't think anybody does it anymore. It's got to be a dying hobby. But then you got AM, FM radio. Those wavelengths are about a meter long, about 3 meters long, maybe. And then finally the wavelengths get smaller and smaller. By the time you get down to gamma rays, you're talking 1 times 10 to the negative 15th of a meter. It's not even, you're almost on the atomic scale at that point. It's pretty crazy. Okay, cool. Take a second here. What would be the wavelength of an X-ray that has a frequency of 4.2 times 10 to the 18th hertz? Give that one a shot. So lambda equals C over F, speed of light, frequency, 4.2 times 10 to the 18th cycles per second. Again, a hertz is actually a cycle per second. Seconds cancel out. We'll get a unit in meters here. And looking like two sig figs, 7.1 times 10 to the negative 11th meters. That's tiny. Even if you want to put it in nanometers, it's so tiny. 7.1 times 10 to the negative 11th meters over 1 meter, 10 to the 9th nanometers. So is that negative second? That would be 0.071 nanometers. Tiny, tiny, tiny. That's the wavelength of an X-ray. Really tiny. Cool.